Today we'll talk about more examples of modules. So far we have seen modules over the ring Z, it's abelian groups, modules over the ring Kx, which are basically vector spaces together with a linear operator. Now let me consider some non-commutative rings this time. And when I say module, of course, I will always mean left module, but today we'll also talk about some right modules. Okay, so let's take example 1, which is the ring. Example 1 is the ring R equals mnk of n cross n matrices with entries in K. So this is n cross n matrices with entries in the field K. So here K is a field, entries in K. So let me fix a field. And of course, if n is greater than or equal to 2, this is not a commutative ring. If n is 1, this is just the field K itself. Okay, and where modules over K are just vector spaces. So I want to look at the same situation for n greater than or equal to 2. And let me give you some examples of modules. So here's V is the set of all column vectors of size n cross 1. So let's take the set of all column vectors of size n cross 1, and here this is still with entries in K. Okay, so this is with entries in K, the base field. Okay, so what are column vectors? I mean they are just matrices of size n cross 1. Okay, now this is this is firstly it's an abelian group, so I want to claim that I can make this into a module over the ring R. Okay, as follows. So observe, already I have addition of vectors, addition of column vectors. So this is an abelian group, definitely. But what I want to do is to define my matrix multiplication. So let me take a matrix A in M and K in my ring R, and I should take an element V from my module. Okay, so I'll take a element V from V. It's a column vector. Now I have to tell you how to define the scalar multiplication of A with the element V of the module. Okay, now there's only one obvious thing we can do here. A being an n cross n matrix, so A looks like this. This is some n cross n matrix, and V is an n cross 1 matrix or a column vector, right? So the most obvious thing you can do is to just multiply the two of them. Okay, so A times V is just defined. So this is the definition. Here's the definition. Define AV to be just the product of the n cross n matrix A with the n cross 1 matrix V. Okay, so usual matrix product if you wish. Now the result is of course an n cross 1 matrix again, or a column vector. Okay, so what is this giving? So let's just denote it as AV, the usual matrix product. The answer of course is again a column vector of size n cross 1, so a matrix of size n cross 1, so that's again an element of V. So this is the definition of the scalar multiplication, and it's easy to check all the axioms. So for example, what are the axioms? So I claim that this makes V into a R module. So what were the axioms? There was distributivity, which says if I take A and I do V plus W, this should become A dot V plus A dot W. Or if I change A, look at A plus B dot V, this must give me A dot V plus B dot V. Now observe, both these are just, they follow from the usual distributivity property for matrix multiplication. Okay, so these are both okay because they come from the distributive property of matrix multiplication. Now axiom 3 was if I take a product of two matrices A and B and I scalar multiplied with V, it should give me the answer of repeated A acting on B acting on V. But again, this is just the associativity of matrix multiplication. So this just comes from the associativity of matrix multiplication, because both sides are just equal to, both sides are just the product. Take the product of the three matrices A, B and V. Okay, and finally the identity. So the matrix ring MnR has the identity matrix I n cross n, and the identity matrix acting on a vector V is by definition their usual matrix product, but of course if you multiply identity matrix with anything you get back V. Okay, so all the axioms are satisfied. So here is an example of a left module. So this is now this space V of n cross 1 column vectors is a left module over the ring Mn of K. Okay, and in fact we can just tweak this example just a little bit to construct a right module. So here's an exercise for you. So instead of V, let's take V prime to be the set of all row vectors of size n. Okay, row vectors of size n, by which I mean matrices of size 1 cross n. Okay, so I mean I should either call them row vectors of size n or matrices of size 1 cross n. So anyway, so this is so you know what these look like. A typical element is a row vector like this. That's a typical element of V prime. And now the claim is that V prime can be made into a right module over this ring R of matrices. Okay, how? Via the following operation. I take a matrix A and I should tell you how to do this scalar multiplication. Well, the definition is this. Just look at the row vector V. So now V is a 1 cross n matrix, and I multiply it on the right by the matrix A, which is an n cross n. So this is V and this is my matrix A. Okay, I multiply it on the right by A, and the answer is again the usual. I mean, by this I just mean the usual matrix multiplication of these two, of V with A, and the answer again is a row vector. Remember, 1 cross n into n cross n, the answer will again be a 1 cross n matrix, right? It will again be a row vector. Now this is a right module, not a left module, because if I take a product of two matrices A, B and I try to act it upon V according to this definition, then this is just the matrix product V into A into B, but that's just the same as what you would get if you first multiplied V with A and then multiplied the answer with B. So in other words, this is what you would get if you took V, you first acted on it by A, or scalar multiplied it by A and then scalar multiplied it by B. Okay, so that's exactly the definition of a right module. So row vectors with this definition form a right module. Column vectors with the usual matrix multiplication form a left module. Okay, so time for another example. So let's take example 2. Now I'll take the ring R to be a group ring. So recall from the lectures on rings that the group ring of a finite group. So let's take G to be a finite group. Its group ring is defined as follows. It's the well, it's firstly it's a vector space, so I need a field as well. So K is a field. So R, which is called the group ring of the group G over the field K. Right. So this is the group ring of the group G over the field K. Was defined as follows. Firstly, it's a vector space. So how do you define R? R is a vector space. It's a vector space over the field K. It's a K vector space. So you start with the K vector space with basis given by some elements. So we were labeling them as 1 sub G. Okay, these are the elements G runs over G. So I take these finitely many basis elements, 1G as G runs over. So this is the set, this is the basis. Okay, and of course that's just in some sense I've only told you how to do addition now. So what is the addition here? If I take, so what's a typical element? Firstly, a typical element of R looks like summation AG 1G. Right? It's a linear combination of the basis. So this is a typical element of R. So let's call it G in G. And to this, if you add another element, be G 1G, G in G. Because the answer is just because these form a basis, I can just add them like this, 1G, G in G. Okay, so that's the operation of addition in this group ring. And recall multiplication can be defined as follows. It's enough to sort of define it on the basis elements. If I take the product of the element 1g with the element 1h, just gives me the element 1gh corresponding to the product g into h. So this was the definition of the multiplication. Of course, to define it in full, you'll also have to say how you multiply two linear combinations. So I take a linear combination like this and another linear combination like this, h in g, g in g. Now I sort of just use this rule above and compute it bilinearly. In other words, I just expand it out in full. Sum over all g in g, sum over all h in h, ag, bh, and 1g into 1h is just 1gh, right? So I'm just recalling the definition from the previous lectures on rings. So this is how the group algebra or the group ring over K is defined. Okay, and as was checked there, it's a ring under these operations. So let's do one particular example here. Let's take a simple example of a group ring. Let's take the group S3, which is the symmetric group on 3 letters. So in one line notation, recall the elements look like this. There's 1, 2, 3, 1, 3, 2. There's 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Okay, these are just the elements written in one line notation. So example, if I pick, say, if I call this as my element sigma, so let sigma denote the one line notation permutation 2, 3, 1. This means that it's a function. So permutations are functions from the set 1, 2, 3 to the set 1, 2, 3, bijective functions. Sigma maps 1 to 2. It's the first entry. Sigma maps 2 to 3. So 2, 3, 1. So this is what sigma does. Okay, so sigma is a function from the set 1, 2, 3 to itself. Okay, so that was our definition of the symmetric group and permutations. Now let's take the ring R to be the ring, the group ring of S3 over this field K. Okay, so K of S3 is our ring R. So recall, what does this mean? It means I have a basis as a vector space. This is a 6-dimensional vector space. It's got basis indexed by, I put 1 sub 1, 2, 3, 1 sub 1, 3, 2, 1 subscript 2, 1, 2, 1, 3, 2, 3, 1, etc. Okay, each element of S3, to each element there corresponds a basis of this space. And the multiplication is the key thing here. It's 1g into 1h multiplies in this particular way. Okay, so let's construct a left module for this ring R. Okay, so I'm going to construct the following left module. So let me tell you what this space M is going to be. M is just a space K3, okay, by which I mean the 3-dimensional vector space over K, which I will think of as column vectors of size 3. So let's think of K3 to be the following set consisting of all column vectors x1, x2, x3, where xi's are all elements of K. Okay, so this is a 3-dimensional vector space, if you wish, over K, over the field K. Now I claim that this set M can be made into an R module. Okay, so I have to define the scalar multiplication. Observe, M already has an addition, right? This is just all column vectors. It's in fact a vector space over K. I certainly has an addition. Okay, under that addition, it's already an abelian group. So that part is okay. It's only the scalar multiplication that we have to define. So let's define it in the following manner. So we say that, so we now define. So I have to tell you, given an element x1, x2, x3 of my module M, of my space M, I have to tell you how to scalar multiply it with every element of my ring R. Okay. Now let me tell you for a start how to scalar multiply it with a particular basis element of my ring R. This special element 1 sub g for all g. So let me take some sigma. Okay, so let me take sigma to to be some element of my group S3. For this element sigma, I will now tell you how to scalar multiply the vector x1, x2, x3 by the ring element 1 sigma. Okay, so what is this? So here's the definition. This is defined as follows. It is x, so it permutes the x's just like whatever sigma would do. Okay, so this is x sub sigma inverse 1, and we'll just see why the inverses are required in a second. So I put sigma inverse to x sub sigma inverse 3. Okay, so this is my definition. Each vector x1, x2, x3 column vector is mapped to the vector x sigma inverse 1, sigma inverse 2, sigma inverse 3. So let's do an example. This is for any sigma. So maybe I should, so this is for all sigma in S3. Let's take that particular sigma that we looked at in the previous one. Let's take this example. Okay. So if I take this particular sigma 231 example, if sigma is 231, what will 1 sub 231 do? Okay, when it acts on x1, x2, x3? Well, the answer is it will map it according to this formula. So recall what was sigma doing. Sigma was mapping 123 to 231. Okay. So in particular, that means if I take the inverse of sigma, the inverse map, then sigma inverse will map 1 to 3. Okay. So let's write that down. What does sigma inverse do? Sigma inverse maps 1 to 3. Okay, so let's go back up again. Sigma inverse of 2 is upstairs here is 1. Sigma inverse of 2 is 1. And sigma inverse of what's left? Sigma inverse of 3 is 2. Okay, so that's what it does. So let's just see what that means. So this is x 3 on top, x1, x2. Okay, so the element 1 sub 231 acting on x1, x2, x3 gives me x3, x1, x2. Okay, so you see what it has done. It has taken x1, the element x1 here, which occurs in the first place, and it has moved that x1 from the first place to the second place. Okay, so remember that's how sigma acts, right? The action of sigma, let's write sigma here. Sigma maps the number 1 to 2, maps the number 2 to 3, and 3 to 1, right? So now this action here, you should remember it as follows. It takes the element in the first position and moves it to the second position. Okay, now sigma of 2 is 3, so the x2 which is in the second position is now moved to the third position, and 3 which is in the third position, x3, gets moved to the first position. Okay, so this is what this particular element 1 sub 231 does. More generally, if I take 1 sub sigma acting on x1, x2, x3, it will act in the same way. So I need to put the inverses here for a reason. We'll see soon. It's to make it a left module rather than a right module. But the basic idea is that it permutes these three components x1, x2, x3 sort of the same way that sigma permutes the numbers 1, 2, and 3. Okay. So I have defined this action. Of course, I have only defined it on the basis elements. It's sort of clear what I need to do in general. So more generally, I need to complete the definition by saying, if I have a linear combination of these guys, C sigma 1 sigma, if you wish, sigma running over G, then that acts on a vector x1, x2, x3. I just expand this summation here, x1, x2, x3. The answer is just summation sigma, C sigma, and 1 sigma acting on this vector, which I know is x sub sigma inverse 1, x sub sigma inverse 2, x sub sigma inverse 3. Okay, so I complete the definition in this way. This is the full-fledged definition. So this is for C sigmas. So what are the C sigmas here? C sigmas are just elements of K. So they are just for all constants, for all elements C sigma of K. Okay, and for all x1, x2, x3 also in K. So this is also for all x1, x2, x3 running over K. Okay, so this is the full definition of the scalar multiplication. So now we need to check that this is in fact a module, okay, which means I need to check all the axioms again. So let's check that claim this makes M into a left R module. Okay, and let's prove this. This just involves checking all the axioms, and axioms 1 and 2 as usual are rather easy, so I'll leave that for you to check, just the distributivity properties. So let me check axioms 3 and 4. So axiom 3 is important. That's the one which ensures it's a left module, not a right module. So let's compute. So suppose so what do we need to check for axiom 3? I need to check that if I take say alpha acting on the product alpha beta acting on a vector should give me the same answer as successive actions. So alpha beta acting on an element x1 x2 x3 should give me the same answer as alpha acting on beta acting on the element x1 x2 x3, and this should be true for all alpha beta coming from a ring. The ring here, remember, is the group ring of S3, and for all elements x1 x2 x3 coming from my module M. Okay, now in this case, of course I should in general pick alpha beta to be any elements of KS3, meaning any linear combinations. So I should pick, for example, alpha to be something of this kind, beta again to be some such linear combination. But it's sort of enough to check it on just the basis elements for a start, and then if it works nicely there, then taking sums will usually work out nicely. So let me just check it on the basis elements and allow you to check the entire linear combination. So let me just take this simple case. So I will just do it in this simple case, that alpha is of the form 1 sub sigma. Okay, it's just a single basis element. Beta is of the form 1 sub tau. Okay, where what are sigma and tau? There are some particular elements of S3. Okay, so let me check. I will just do this case. I will do this case. Okay, and leave the full summation to you. So let's compute the left hand side. Okay, so what is the left hand side here? It's this guy. So let's compute this. The left hand side turns out to be alpha beta times this. And what's alpha beta here? It's 1 sigma 1 tau. That's the product alpha beta acting on this vector x1 x2 x3. Okay, but 1 sigma 1 tau by definition is 1 sigma tau acting on this vector x1 x2 x3. And that by our definition is just you have to change the x's like this: sigma tau inverse of 1 x sigma tau inverse of 2, the last is x. Okay, maybe I should just write it. So let me just write it on the next page. So this is the same as the vector x sigma tau inverse of 1 x sub sigma tau inverse of 2 x sub sigma tau inverse of 3. So that's my column vector. Now let's compute. So that's one answer. So we have found one answer. So let's do the right hand side as well. So what is the right hand side in this case? So recall the right hand side is 1 sigma followed by 1 tau acting on x1 x2 x3. Okay, so we have to do this a little more carefully. So let me do it slowly. If I take 1 tau first, so let me compute what's on the inside. I take 1 tau and I act on x1 x2 x3. Now when I do that, by definition, this is the vector x tau inverse 1, tau inverse 2, tau inverse 3. Okay, so that gives me some new element. So let me call this element something. Let me give it a name. Let me call it y1, y2, y3. So the three numbers, the three components are y1, y2, y3. So this is just definition, I'm calling it this. Okay, now let's act 1 sigma further on this. Now I take 1 sigma and I try to act on this element here. Okay, so what's that? That's just 1 sigma acting on, so let's, since I've called it y1, y2, y3 for short, let me just use that notation. 1 sigma acting on y1, y2, y3, which by definition is, it moves whatever is in the first component. So it's just y tau inverse 1, y tau inverse 2, y tau inverse 3. So that's my 1 sigma acting on 1 tau acting on x1, x2, x3. Okay, now let's unravel the last step. Let's look at what we got as the answer. So let's look at this answer here and see what that becomes. Now remember, y tau inverse 1. So what is y of anything? yi is same as x sub tau inverse of I. Okay, so when I say y of tau inverse 1, I made these taus instead of sigmas. So sorry, recall, I'm hitting it with a 1 sigma. So sorry, these should all be sigmas instead of taus. So let's make that change. So this should be actually y sigma inverse 1, y sigma inverse 2, y sigma inverse 3. Now what is y of any index is just, from here I observe it is y, it's x sub tau inverse of that index. Okay, so let me just remark, let's observe that if I want to compute y sub I just have to take x sub x inverse I. So this is the bit that one has to be a little careful about, x sub tau inverse I. X sub tau inverse I. Okay, so this is for I equals 1, 2 and 3. Okay, so let's plug that into the next page. So I conclude that if I take 1 sigma and then act it on 1 tau on x1, x2, x3, the answer is x sub, let's go back up, it's y sub sigma inverse 1, but y sub sigma inverse 1 is x sub tau inverse sigma inverse 1. Okay, so it is tau inverse acting on sigma inverse 1. Same thing, x sub tau inverse acting on sigma inverse 2, and this becomes x sub tau inverse acting on sigma inverse 3. Okay, so what does that mean? Finally, I conclude that this is the same as x sub, so tau inverse sigma inverse, remember, is just sigma tau the whole inverse, x sub sigma tau the whole inverse, and x sub sigma tau the whole inverse 3. Okay, so that's the same as what we got on the left hand side. Okay, so this proves that axiom 3 holds. In other words, it's a left module. Axiom 4 is again easy, so let me leave axiom 4 as an exercise. So you just got to check what the identity element is. Recall, the identity element of this ring R is just the element which is called 1 sub the identity. Okay, so exercise is use the fact that this is the multiplicative identity of this ring. Okay, so the key point is that this inverse is the little twist here that that's required to make it work out right. And little exercise again, if you didn't put an inverse there, exercise, if we define the action as follows: 1 sub sigma acting on x1, x2, x3 to be the same formula without inverses, x sub sigma 1, x sub sigma 2 and x sub sigma 3. If you did this, then what happens? Well, then m becomes a right module. Okay, so that's the interesting bit here. Okay, excellent. And my final example for now is a sort of a general one. So this is if let R be any ring, then R actually is a left module over itself. In other words, i.e., so what do I mean? I can take my module to be my ring itself, to be my underlying set of the ring. With what addition do I take? Well, I take the same addition of the ring itself, with plus being the ring addition. So I just think of the ring under addition as an abelian group. Okay, so that's my underlying abelian group of M. And I have to now tell you what scalar multiplication is. And scalar multiplication is defined as follows. Well, I just do left multiplication. And scalar multiplication is defined via the following. If I take an element alpha in R, and if I take an element x in M, so remember M is actually R again, then I define the scalar multiplication alpha x to be just the product of these two elements. So this is now the product in the ring R. Just the usual multiplication. Observe, both alpha and x are actually elements of R. So I'm just using two different notations for R to say, I think of one as being the sort of the scalars and the other as being the module itself. So that's the first thing one can do. You can think of a ring as a left module over itself. And again, just like we did in the two previous examples, you can change left to right in the following way. So this is a left module, but I can as well define an alternate right module structure as follows. So I can change left to right if I do the following. I define this operation alpha dot x differently. I now define alpha dot x. It becomes a right module. So R is a right module over itself via, well, the same addition, but multiplication is now multiplication on the right. So this is for all alpha for all x in R, which is the same as M. Okay, so under the right multiplication operation, if I take the scalar alpha and I multiply it on the right of x, then that gives R the structure of a right module. Okay, and if I multiply the scalar alpha on the left, it gives me the structure of a left module. So R is in fact a module, both a left and a right module over itself. Okay, so we have seen in some sense three examples of modules, which are, well, three examples of left and three examples of right modules. A remark on notation. So we keep talking about left and right modules. Now recall when we say that something is a right module over a ring R, just means that I have elements alpha for all alpha in R. So M is a right R module, just means I have a notion of, so there is a scalar multiplication, there is a notion of scalar multiplication, and we denote this scalar multiplication by, so our notation for the scalar multiplication is like this, right? So we always say, let's say alpha acting on x is the scalar multiplication, and it satisfies the other axioms are the same. This axiom 3 dash that we talked about, that's the key here, which is if I multiply alpha and beta and then I scalar multiply it with x, then the answer is beta scalar multiplying alpha scalar multiplying x, right? That's the order. Now looking especially at the examples that we have done this time, the three examples, especially the last one where R acts on itself on the right by right multiplication in some sense, an alternate notation. So here is a more conventional and alternate notation for this scalar multiplication. So so if you have a right module, then we usually write the scalar on the right of the vector. Okay, so we write more conventionally usually in the following order. So this is only for right modules. So if M is a right R module, then the scalar multiplication by alpha, okay, scalar multiplication of X by alpha if you wish, scalar multiplication of the element X in M by the scalar alpha in R is denoted as follows. We say X scalar multiplication alpha. Well, alpha is thought of as being a scalar that multiplies on the right. Okay. Now, why is this? It's slightly strange if you're used to seeing scalars, thought of as being multiplied on the left. Now, why is this alternate notation somewhat better? Because it captures this axiom 3 prime notationally in a more pleasing way, which is that X scalar multiplied by alpha beta is, well, what does this say? It says if you want to scalar multiply X by alpha beta, you must first multiply by the scalar alpha, then by the scalar beta. So this is in our new notation, it just becomes this: X first you scalar multiplied by alpha, then by beta. So in some sense it flows in the same order. Okay, so you will usually see right modules written in this way, where the scalars are thought of as sort of acting from the right. Okay, but of course, I mean, this is just a question of notation. There is nothing fundamentally new happening here. You could, if you choose, just choose to do it the way we did it, that the scalars act on the left, but the composition rule is sort of switched, that when alpha beta tries to act on X, you must first act alpha, then beta. Okay, or you could choose to just use this usual notational convention where the scalars are thought of as somehow coming from the right, and in which case it's easier to remember the order in which it flows. Okay.